Of the Electrical Engineering and Computer Science Division at UC Berkeley. He was educated at Oxford and Stanford and joined Berkeley in 1986 as what I think was the youngest professor in the history of the UC system. He holds the Smith-Zadeh Chair in Engineering and is also an adjunct professor of neurological surgery at UC San Francisco. Stuart has been recognized by many awards for his work, including the Ichkai Computer and Thought Award, the ACM Outstanding Educator Award, and the Chair Blaise Pascal in Paris. And he's a fellow of AAAI, ACM, and AAAS. It's very hard to think about a more suitable invited speaker for this joint session because Stuart made many seminal contributions to work that's relevant to both communities, including other communities, and was among the first to ground the concept of meta-reasoning and control of search in a deep formal framework. He has also published an acclaimed textbook that modernized AI education and is described by Amazon reviewers as the AI Bible, just terrific, truly beautiful book, the book that made me love AI, and most importantly and relevant to the ICAPS community, it's described as a landmark. So please welcome Stuart Russell.
Thank you, Shlomo. Thank you to the organizers for the invitation. Shlomo forgot to mention that he's one of my most distinguished graduate students. And he's listed among the various collaborators that contributed to this work. So sometimes when I give this talk, I use this other title, Play and Win in 20 Trillion Moves, and in a minute you'll see why I give that title. I should also point out that joint work with usually means real work done by, and in that case this is absolutely true. So I'm going to give you a less than 20 trillion move problem to solve. Give you about 30 seconds to think about this one. Just put your hand up when you figured out the correct first move. Okay, 1, 2, not many. Okay, so this is a small problem, right? There's only 20 odd objects. There's only 64 places, it's all discrete. It's only 2 time steps, and we're still having trouble with this problem, right? But let's look at the problem that you really solve in your actual life. So if you're fortunate enough to live for 100 years, you have about 640 muscles, and in principle you can change their actuation levels at about 10 hertz. So that adds up to 20 trillion actions in your lifetime, all right? So there's some kind of mismatch going on here because we seem to manage okay with our lives. We don't necessarily plan out our whole lives, but we plan out big chunks of it down to some level of detail. Since this is a talk that includes meta-reasoning, it's worth mentioning that we can do things besides actuate our muscles. We can actuate our brains as well. We can decide to think about things, which changes our brain state on purpose, as well as just changing the physical state of our bodies. So not only do we have this much greater timescale, much greater number of actions, but the world we work in is much bigger than the chessboard, right? It's huge, it's continuous, it's all the things that make decision-making intractable or undecidable, and it's all those things in spades, and still somehow we manage. So there must be something else going on besides forward search using primitive actions. So if you learn nothing from this talk, please just take that away. There's more to life than forward search using primitive atomic actions. Okay. Right, so there are lots of things besides that, and hierarchical structure I think is the most obvious, and Simon pointed this out decades ago, many other people have pointed it out, that we don't plan and reason and deliberate in terms of just the primitive actions. And we have very deeply nested hierarchies of behavior. And those hierarchies simplify the decision-making problem, because if in the hierarchy I've decided to say the word tongue, right, then the way I say the T at the beginning of that tongue does not depend on, for example, the current price of tea in China. Right? It doesn't, in fact, it depends on almost nothing about the world. So all those people who are busy building policies pi of S, where S is the state of the world, actually you don't have to care about almost all of S, right, for most of the decisions you make. So that's a marvelous thing. In fact, if it wasn't that, it would be completely hopeless, right? So it's as if when you were playing chess, you only had to pay attention to one of the squares, and the rest of the board didn't matter, right? Wouldn't that make life a lot easier? And that's how it is with hierarchical decision-making. They also give you the scale. So there's modularity and there's scale. So coming to this conference is about 3 billion actions. And yet you can choose to do it, right? Without having to figure out exactly which 3 billion actions you're going to do. You can still choose to do it. And that allows you to make plans over long time scales and cuts down the amount of computation enormously. So this is something that is clearly one of the keys to human intelligence and one of the keys to AI. When you talk to the deep mind guys, right, they announced this huge breakthrough that they could play all these Atari video games using deep learning, but they can only play the ones that don't require very much look ahead, right, where the short horizon rewards guide behavior pretty well. As soon as you get to Pac-Man, where you have to maybe go 30 or 40 things to go find the whatnot you have to eat or the ghost you want to trap, it fails, right? And it fails because all they can do is make decisions in terms of primitive actions. And they are fully aware of that, and they tell me that they've nearly solved the problem of automatically generating high-level actions, and then they're going to take over the world. So I've been trying to understand this. You can see there's a long list of papers going back to 1997, so I'm going to try and cover all of those in this talk. Right, so let me, but I'm going to give the talk actually in reverse chronological order. I should say it goes back to '88 when we first started working on meta-reasoning. But the first in description is the last in coming to being, as Aristotle said about backward chaining planning algorithms. So here's roughly what happened, right? So meta-reasoning we did back in the late 80s and early 90s. And in fact, we started up again recently with working with Nick Hay and have some more results. When we started to understand hierarchical behavior, it was in the context of reinforcement learning and MDPs. And we wanted to add to that the capability to do look-ahead. So not just learning a Q function and then making decisions based on the Q function, but actually combining look-ahead with a learned value function, because that gives you much better behavior. So we tried to do look-ahead using the high-level actions that were built into our hierarchical reinforcement learning framework, and we couldn't find out how to do it even in the classical setting. So we had to go back and figure out how to do it in the classical setting, which is simpler and more straightforward. So that's why it's in backwards order. Okay. So look ahead is great, right? We all know that if you look ahead k steps in chess, you play much better than if you look ahead one step. All right. But if you try to write an ICAPS paper by just enumerating possible sequences of characters starting with A, you don't get very far. This is, it sounds like a great idea to do, look ahead as deep as you can. But it's just a complete non-starter for doing something like writing a paper. Okay, so we want to get abstract look ahead. We want to think about actions that correspond to big chunks of stuff, and then build our look ahead on top of those actions. And Rich Korf had a very nice paper where he just showed in a very simple extensional context. His metaphor was sort of freeways and side streets. And then layers and layers and layers of smaller and smaller side streets, that you can get exponential speed up, that planning in a well-constructed hierarchy of abstractions is linear time even when you have an exponentially large state space. Okay, so let's not get too complicated about what high-level actions are. We'll use the very simplest classical HTN kind of definition of a high-level action. So the setting is there are some primitive actions, and those are fixed and given. We know what they are. And a high-level action has possible refinements. So you can refine a high-level action into a sequence, and the elements of that sequence can be primitive or other high-level actions, including the high-level action itself, so it can be recursive. In HTN planning, we normally assume that the only thing you're allowed to do is produce a sequence of primitive actions that's derivable by refinement from the top-level act, which is the most general. So I know there are variants. In fact, there are posters on variants where you're allowed to insert additional actions and so on, but I just want to keep things very simple. So for example, here is my highest level action to act. And if I'm trying to go somewhere from my house, let's say I want to go to New York, I might try going to San Francisco Airport, or I might try going to Oakland Airport. And then to go to San Francisco, that's a high level action. I could choose one way of refining that is to walk to the BART station, which is the subway, take the subway to SFO. And then maybe I can figure out exactly how to take the subway to SFO, where I'm going to buy a ticket, et cetera, et cetera. Or I could maybe try refining the Oakland plan instead. So this is how HTN planning works, and traditionally what you do is you simply expand this tree down until you get to primitive sequences, until you find a primitive sequence that does in fact achieve the goal. Okay. So what we would like to do with high-level planning to get this exponential improvement is simply to be able to come up with high-level plans that we are sure are correct without having to go all the way down to primitive actions. Okay, and that's how you're going to get the exponential speed up. To do high-level planning, to say this sequence of high-level actions achieves the goal, you have to have a model, a transition model that describes what the high-level actions do. Okay, so when we were working on the hierarchical reinforcement learning in the MDP setting, we thought, okay, let's go look in the HTN literature and see how they describe high-level actions, and then we'll probabilize that, right? We'll just add probabilities to it, and everything will be fine. So I sent my students off, and they came back and said they couldn't find anything. I said, just look harder, come on, don't be ridiculous. But then one of them came back with this quote from Drew McDermott. So Drew, I don't think Drew's here today, but he tried to set up an HTN planning track back in 2000 as part of the planning competition, and he gave up. And this is why he gave up, that no one had ever figured out the semantics of high-level actions, right? The high-level action is defined in terms of its possible expansions into lower-level actions, but there's no statement as to what the high-level action does, and so there wasn't agreement on how you would provide information about high-level actions to the planning systems. That means that you can't come up with correct high-level plans, which is a pity. And it's not as if people hadn't tried. So that there's a very well-known concept called the downward refinement property. And what that property says is that if you have a high-level plan that claims to achieve the goal, then there is a way to refine it into a primitive sequence that does achieve the goal. Right? So that's the DRP. And if you could have this property, then that would be great, right? Because then you would, as soon as you find a high-level plan that claims to achieve the goal, you can then commit to that. You no longer have to backtrack. That choice is fine. Then you just have to figure out how to make that plan work. Okay. And then Fahim Bacchus and Qiang Yang looked at this and essentially gave up. They said they looked at lots of HTN planners and they said, look, it's violated left and right in the way the hierarchies are defined and the annotations that are written down purporting to describe what the high-level actions do. The DRP is violated almost everywhere. Okay, but the only way it can be violated is if you tell lies about the high-level actions. So my recommendation is don't lie, and then things work better, right? Because if you wrote some annotations on the high-level actions, and the high-level actions given those annotations claimed to be able to achieve the goal, but actually they couldn't, then obviously your annotations were false, right, by definition. So if you just write things that are true, it has to be the case that the DRP will hold. Okay, and this is, it's hardly worth the name theorem, right? It's just so obvious. So that just gives you this problem then, okay? How do you say anything that's true about what the high-level actions do? So this is where we came up with the idea of angelic semantics. The word angelic came from the programming language community, where they consider two kinds of non-determinism. There's the standard kind, which we're familiar with in planning when we talk about non-deterministic actions. Those are ones where nature will choose which of the possible outcomes happens. And if you want a plan that works, it had better work no matter what nature does. Okay, so that's called demonic non-determinism, whereas angelic is the other way around. You're going to get to choose. And this is the sense of non-determinism in NP, right? So NP means that if you choose perfectly, then you can solve this problem in polynomial time. Okay, and that's the notion that we want. So this is angelic non-determinism. Okay, so let me just very briefly illustrate what it means. So I've got a little state space with, I don't know, 15 states in. There's a state S0, which is the start state. There's a goal state at the bottom. And we've got to get from S0 to the goal state. Okay? And the key thing, in fact, this word itself really helped. This is the word that control theorists use for a somewhat similar concept. But once you start thinking about the reachable set of a high-level action, what does that mean? It means that this is the set of states that you can reach under some refinement of your high-level action. Not under all refinements, but under some refinement. And because you're choosing which refinement, then that set, that reachable set, which is the union of all the states that can be reached by any refinement, is in fact the set that you care about. Okay, so if you just remember reachable set, you can probably reconstruct all the rest of what I'm going to say without having to read the paper. Okay, so here's a high-level action, H1, and if we apply it in state S0, its reachable set is either S0 or the state below S0. So maybe there are two ways to do H1. One of them has no effect. One of them has the effect of getting to the state just below S0. Okay? Another high-level action can be applied. So if I apply H2 to the state S0, then I get to one of those three states, depending on how I do H2. If I apply H2 to the other state, the one just below S0, then I get to those four states in the vertical bar. I notice that one of those includes the goal. Okay? So now if I take H1 and H2 together, right, then the reachable set for the H1, H2 sequence is that T-shaped region. And the T-shaped region includes a goal state, right? In fact, it doesn't have to include all the goal states. As long as it intersects the set of goal states anywhere, then the plan is guaranteed to work. Okay? And that's why this notion of reachable is so helpful, because it means you can reach anywhere in that set. You just have to figure out how. Okay? So H1, H2 is a high-level correct solution to this problem. Okay. So I think I already mentioned this, right? So it's the dual of the standard notion of non-determinism that we're using in regular planning. Okay. Once you found H1, H2, then you have to figure out which of the choices of refinements for H1 and for H2 will actually get you to the goal state. Okay. But you don't have to consider other high-level plans because you've already found a solution. All right. So the rest of this is mostly just turning the handle, right? So the first thing you have to say is, well, how are we going to describe these reachable sets, right? So there I just enumerated them for you, but obviously that's not going to work. In general, we have to have some kind of intentional description of preconditions and outcomes. And the simplest thing we could think of is just to extend strips notation so that in addition to things that an action definitely makes true or definitely makes false, which is already in strips, or in SAS you can have flipping. You also want to have the possibility that some literals are added under some refinements but not others. Some literals are deleted under some refinements, but not others. Some literals you can have either way, right? So you can control which way they come out depending on how you choose your refinement. So there's a set of these additional literals. So you can think of add as plus and delete as minus, and then there's plus and minus, minus and plus, plus twiddle, minus twiddle, and so on. They all have appropriate semantics in terms of these kinds of possible effects. So for example, if you're going to go to San Francisco Airport, all ways of going to San Francisco Airport get you to San Francisco Airport. So at SFO is a normal add condition. But if you drive, then your car will be at SFO. If you take the BART, then your car will be at home. Okay, so car at SFO is a possible add for going to SFO. And if you don't want to think about how exactly you're going to go to SFO, you can just keep that in mind. It's possible if, for example, your wife is coming back the next day and she needs the car to get home, then you could drive to the airport and leave it for her to bring back. Okay, and that would work as a plan. The next thing that occurs to you is that because a high-level action in a deep hierarchy will have maybe exponentially many ways of being implemented, and if you think about all those reachable states as a function of the input state, that may be a very wiggly reachable set that's very hard to describe, may in the worst case have an exponentially large description. You need to think about approximating those sets. So in the usual time-honored tradition, we put upper and lower bounds on those sets. And in the cost-based version of this, you also have upper and lower bounds on the costs of the states in those sets. That introduces an additional possibility. So previously, by analyzing the reachable set, you can say, yes, if the goal intersects the reachable set anywhere, then the plan definitely works. If it doesn't intersect it, then it definitely doesn't work. Right now, you've got a third possibility that the plan possibly works. And you don't know whether it works or not because you haven't refined it enough. You're using, because it's still at a very high level, you're using a very approximate, loose upper and lower bound description of what the high-level action does, and therefore you need to refine further. And this is a very natural thing human beings do all the time. So in terms of algorithms, we can write algorithms that are, in the usual senses, sound and complete, and optimal, whether they're offline or online algorithms. And then we did a few experiments. I'm not just going to show you a couple of results. We came up with a version of the blocks world called the warehouse world, where the blocks actually have locations, and the warehouse has a ceiling, so you can't stack blocks higher than the ceiling, and if you stack blocks up to the ceiling, then you can't get through that pile to the other side of the pile, so you have to undo it before you can get to the next location. So this is a convenient way of actually generating problems that have much longer solutions than most blocks world problems. And it means that some of the simpler ways of solving blocks world problems don't work. So it actually is a more interesting kind of blocks world. And more realistic. You could call it the Home Depot world. It's actually quite a good model of the Home Depot. So here's the runtime for a 5x8 world. So that means there are, I think it's 5 high and there are 8 locations in a line. And the solution, whatever problem it was, is 90 steps. And essentially, with very, very simple high-level actions. So the high-level actions are to pick up a block and move it somewhere, and to move the gripper from one location to another. So those are the 2 high-level actions. We don't tell it how to move the gripper from one location to another. We just tell it to move from one location to another. You move, and then once you get there, then you're done. Okay. So there's very little structure, but just that structure is enough to go from run out after about 3 hours of time on the standard HTN planning algorithms, and down to less than a second with the actual descriptions of the high-level actions that I gave you. We also looked at the online search case, and we compared, so we have an online hierarchical learning real-time A-star, so Angelic hierarchical learning real-time A-star algorithm with the same abstract actions, and again, we get considerably better performance. So here we're showing on the on the x-axis, the number of plan refinements that you're allowed to do per physical action. Okay, so in real-time search, you do a physical action after a certain amount of deliberation, and you bound the amount of deliberation that you're allowed to do. And you can see that the Angelic version is getting, with the same amount of computation, solutions that are 2 or 3 times shorter than the solutions found by the classical LRTA star algorithm. We came up with an even more deviously and nicely scalable domain called the nav switch domain, which is a grid navigation problem where in certain squares there are switches that you can flip, and when you flip those switches, it changes the cost of vertical versus horizontal movement. And this turns out to be a difficult problem to solve and very nicely scalable. And LRTA star essentially can't solve this problem at all, and the hierarchical version can basically do fine. It solves it immediately. And the only action we had there is navigating from one switch to another. Okay. So, summary of part 1. We're not going to get anywhere in AI unless we have temporal abstraction, meaning thinking about actions that are, when executed, going to occupy a large amount of time, many, many primitive actions. And with these angelic descriptions, it seems like we can get what we hoped for from hierarchical descriptions of actions. We can get that ability to come up with provably correct high-level plans. Okay, so now let me go back in time and talk about some work we did on hierarchical reinforcement learning. So this was one of those cases where if I'd walked across the road and talked to my colleague Praveen Varaya, I could have saved myself about 18 months of work. So Ron and I and some other members of the RUGS group spent many sessions trying to figure out how to get hierarchy into MDPs. But in fact, Praveen had already worked this out 20 years before. So the basic idea is a very simple one, right? So you start with some base MDP with its primitive actions. On top of that, you can define what are called choice-free actions. So these are temporally extended actions. They're very much like options in Rich Sutton's framework. So there's something where you start them, they run without making any choices, and they stop according to some condition, whatever you want. The states where they stop, you're going to have to make another choice. And if you think about those as like, getting on a freeway and then following the freeway until you get to an off-ramp and then getting off on the off-ramp, right? It constructs a new MDP with these sort of mega actions, except that because the mega actions take extended amounts of time, it's going to be a semi-Markov decision process, meaning that the number of steps that it takes to execute the action is more than one and may also be unpredictable. And because you have discounting, that does matter. So you get a semi-Markov decision process in terms of the extended actions and the choice states that you can reach when any one of those extended actions stops running. Okay, so then once you have that semi-Markov decision process, you can apply all the standard techniques. You can do reinforcement learning, you can do value iteration, and so on. That's actually a big step forward because prior to this work, most people were trying to do hierarchical reinforcement learning by state abstraction, meaning taking the state space, cutting it up into chunks, and then treating each chunk as if it were a single state. And unfortunately, when you do that, you lose the Markov property. And then you can't do value iteration, you can't do reinforcement learning. Your algorithms oscillate, they produce bad policies, all kinds of unpleasant things happen. So keeping that Markov property was a key step. So the work I did with Ron Parr extended this idea of sort of a two-layer primitive and then extended actions to the notion of hierarchical abstract machines. So they're essentially non-deterministic finite automata where a transition in the automaton can invoke a lower level automaton. It can also be recursive, so it can invoke itself again. And what we showed was that when you take the hierarchical abstract machine that you're using to describe the hierarchical structure of behavior, so it's a little bit like the HTN refinement network, and you combine that with a domain, again, you get a semi-Markov decision process, and you can do reinforcement learning, and you can get amazing speed-ups in how quickly you can learn to solve problems using reinforcement learning. Around the same time, Rich Sutton came up with his options framework, and Tom Dietrich came up with the MaxQ framework, which is very, very similar to the HTN hierarchy that I just described. And then a few years after that, David Andre, his thesis was about the notion of partial programs. So instead of hierarchical non-deterministic finite automata, we said, well, what's wrong with programs? Programs are great for describing what to do. So why don't we have programs, but when we're not sure what to do, we just leave the choice blank, right? And then that's the non-determinism in terms of how the system is supposed to behave at that point. And then the reinforcement learning process can fill in that blank as a function of the state of the environment and the state of the program. So that led us to a language called ALISP, which I will illustrate in a second, and then a few years later, concurrent ALISP, where we can do multi-body planning, not multi-agent, but multi-body planning using the same ideas. So let's have a look at an example. This is what used to be called Warcraft and was then called Freecraft, and then was called Strategus when Microsoft objected to the word Freecraft on trademark grounds. So, so in this world, it's the usual God game where you're controlling a bunch of units and you're producing technologies and facilities and collecting resources and building armies and defeating your opponents. So here, it's just a very simple scenario. We have a base, and that's over here. We have peasants that go off to the forest or the gold mine and collect wood or gold and bring it back to the base. So let's just imagine a simple thing where we have to gather 10 pieces of gold, 10 pieces of wood, and so we're going to give you a reward every time you drop off gold or you drop off wood back at the base. There's a cost of living. There's a penalty for crashing into other peasants as you walk around. And this is a relatively simple problem to describe. Unlike a lot of problems, it does have a fairly large action space. So if you have n peasants in the environment, then you have 7 to the n possible actions at each time step. So that's why these kinds of games are actually much, much more difficult than typical board games. So how do we do this with the partial program framework? So we provide a partial program that describes what we know about how we think the behavior of the peasant should be structured, or the behavior of the game as a whole. Okay? If we don't know anything, that's fine. Then you provide a very simple partial program. If you know more, you can provide more information. The learning algorithm then takes the partial program, interacts with the environment, and comes up with the completion. So it turns the partial program into a standard complete program where all the choices are now replaced by, in fact, in this case, Q functions, where the Q function depends on the state of the environment and the internal state of the program that it can use. And what you would like to have happen, and in fact the theorems in the papers do show this, is that the learning process converges to hierarchically optimal behavior, which means the best behavior that you can get that's consistent with the partial program that you provided. So let me just illustrate this with a couple of programs. The first one is the program where you know nothing at all. Okay? So, and you have a single peasant. So the program says loop forever, choose one of the available actions. Okay? And we're not going to tell you which one it is. So this is the partial program that represents an ordinary MDP. Okay? Where you just have a set of actions and you can choose one. But we actually know more than that, right? I don't have to be an expert in traffic or optimizing paths or any of that to say that I want the peasants to go get some gold and get some wood, right? I'm not interested in peasants who just go round and round and round in circles doing nothing, who just bump into each other like this. No, that's not what I want, right? I want them to go get gold, go get wood. right? How they get it, where they're supposed to go, I don't know, right? So we're going to give them a choice, okay? So this is the single threaded, so we've got one peasant to control, right? So we're going to give this peasant a choice, right? You're going to go and gather some wood. When you come back, you're going to get another choice. Or you can gather gold, and when you come back, you're going to get another choice, right? Which one you should do, I don't know. I don't know how far away the gold mines are. I don't know how far away the forests are. I don't know how much gold and wood we have right now. It's going to depend on all those things, and the system's going to have to learn that, right? But it's reasonable to say you should get some wood or you should get some gold, okay? And it's also saying that there's no point going halfway to get some wood, changing your mind, coming back, and then going to get some gold, right? So we're actually ruling out some behaviors just with this statement. Okay, so let's have a look. So gathering wood and gathering gold are very similar. So to gather gold, right, there's a bunch of gold mines you can choose from. So you choose one. So with choice means that you're going to choose a variable whose name is going to be dest from this list. Okay, so now dest will be bound to some gold mine. We don't know which one it's going to be because the agent has to learn how to choose it. Okay, then you're going to navigate to the destination. Okay. When you get to the destination, because it's a gold mine, you're going to do the get gold action. Okay? Then you're going to navigate back to the base, and then you're going to drop it off. Right? So that's what we mean by getting gold. Okay? We now have to tell the system how to navigate. Well, I don't know. I don't know the map. Right? I want to provide a peasant program that works for any map, so I just say, okay, to navigate to some destination, when that destination is the position, then you stop, right? Otherwise, you choose to move. You can move north, south, east, west. And we allow no-op as well, because we'll see later when we have more than one peasant, sometimes you need to wait for the other peasant to go by. So we're allowing no-op in navigation. Okay? So you're going to choose one of those actions. Its name is going to be move, and then you're going to emit that action as the actual physical action done by the peasant. Okay, so that's what we tell the system, and then the learning process runs. So there's two parts to the state, and the physical state, you already understand that. But there's also the program state. And the program state consists of everything that, you know, if you remember taking your programming language class, everything that defines the current state of the program. The program counter, so where are you in executing the program, everything that's on the call stack, and any global variables that you were sinful enough to define. Okay, so how do we do this, right? Well, once again, we just set up a semi-Markov decision process with this more complex state space consisting of the physical state and the internal state of the program. And then we run reinforcement learning on that semi-Markov MDP, and we learn a Q function that we can then use to make decisions at each of the choice points. Okay, so anytime the program counter is at one of those places which says choose or with choice, then the Q function will give a value for each of the choices, and you just pick the highest one. Now, if that were all there was to this, it wouldn't be very interesting. The really interesting thing about this is that the structure of the program lends itself to a decomposition of the Q function in much the same way that a structure of a Bayes net decomposes a probability distribution into small pieces, each of which depends on a small number of variables and can be learned from a small amount of data. Exactly the same thing applies here. We have an additive decomposition of the Q function, first of all by subroutine structure. So, for example, while you're navigating, right, the Q function for navigating doesn't depend on how much gold you have in the bank, right? Because you're just trying to get somewhere. You don't care how much gold you have in the bank. All that matters is where you are relative to your destination. Okay, so that makes that piece of the Q function very easy to learn, and means that the whole reinforcement learning process works much faster. We can also decompose it, as we'll see in concurrent day Lisp, across the concurrent threads of the program. If you have many peasants, then there are Q functions associated with each of the peasants. If the peasants are operating in little teams, for example, if two of them are carrying a sofa, then there's a reward associated with that pair of of peasants who are carrying out a task as a pair. This also gives you a huge speed up in reinforcement learning. And it turns out that we can arrange the reinforcement learning to be completely distributed among all the peasants, but still guarantee that we get globally optimal solutions. One important thing about this, which is perhaps initially counterintuitive to those of you who, for example, have read my book or have read any other book on MDPs, right? Anyone who knows about MDPs knows that the optimal policy in MDP depends only on the physical state, right? This internal state stuff, all it can do is make a mess of things, okay? It's a fascinating fact that many of the reasons why we do things are not because of the physical state we're in. They're because of something in our mental state. Okay, so for example, while you're navigating to a location, right, the distance from the location is a good heuristic, right? But don't forget, the destination that you have in mind is not part of the physical state of the world, right? If you're driving to work and you say, when I drive to work, when I get to the McDonald's, I turn left, right? That's a perfectly reasonable way to organize your behavior, but while you're driving to work is not part of the state of the world, right? You could be driving in exactly the same place, in exactly the same car, at exactly the same time, and not be driving to work, right? Because in fact, for some complicated set of reasons, you're actually driving to the dentist or some other thing, okay? And so it's much more natural to express these kinds of behaviors in terms of the internal states. If you theoretically, you could probably describe it in terms of the external state, but it would be far more complicated, okay? And so this is a crucial and obvious insight from looking at things this way that would be absent if you just followed the standard theory. Okay, so Shlomo was telling me I don't have as much time as I was hoping. So let me quickly just show you how we handle multiple effectors. So if we have a whole bunch of peasants doing a whole bunch of different things, the way we handle it is simply to spawn threads. So we use the concurrent facilities of Lisp to spawn a thread. Each thread controls one or more effectors. And then when that thread completes, those effectors are returned to the pool, and they're available to be assigned to additional tasks. So here's how we do gathering wood and gold. This was our original program. The only thing that changes is that instead of one peasant choosing between gather gold and gather wood, we have more than one peasant. And every time a new peasant becomes available, we give that peasant a choice, and we spawn him off as a concurrent thread. So now we've got many. We can have 75, 100, 1,000 threads running, controlling 1,000 peasants, and nothing else in the program changes. And magically, somehow all these peasants learn traffic avoidance rules, right? They learn not to collide with each other because their choices are all made jointly. Right? Their choices are made by pooling their individual queue functions, and then we choose the action which maximizes the sum of their individual queue functions. And by that technique, they get globally optimal behavior that avoids collisions. And depending on the exact initial conditions, they either learn to drive on the left or on the right. But you'll see that when you have a lot of peasants, they will all drive on one side of the road, so to speak, whether it's left or right, depends on the initial condition. So let me just give you a couple of empirical results. So here's on the x-axis the number of learning episodes that goes up to 200,000 learning episodes, and on the y-axis is the quality of the policy that's learned. So if you just try on this problem, this is 15 peasants gathering, I forget how many gold and wood pieces. So it's a fairly crowded world, 15 peasants. With standard reinforcement learning, just never learns it at all. We couldn't, we ran for much longer than this, millions and millions and millions of trials. We could not get it to learn how to do it. If you simply provide the partial program, which says gather gold, gather wood, navigate, then you get the blue line. So it actually gets a decent behavior fairly quickly. But this is without the additional process of decomposing the queue function into its component parts. If you do the thread-wise decomposition across the peasants, you get the green line. If you combine that with the temporal decomposition by subroutine structure, you get the black line. Okay? So all of these additional decompositions of the Q functions allow you to scale up to more peasants. And we were able to run with 100 peasants fairly successfully. If I had the video, I would show you this, this video. So this was a much more complicated scenario where multiple peasants have to collect a bunch of stuff. They have to build a barracks. The barracks have to produce soldiers. The soldiers have to go off and fight a war with an enemy. The entire thing is 65,000 time steps of primitive actions. So it's a decent, it's not 3 billion like coming to ICAPS, but it's a decent length of horizon. And it took about 2 hours to learn, and it learns a policy that's better than the one that the expert human player was able to come up with for the same task. Okay, so quick summary, partial programs give you a very powerful and general language for specifying what you do know about how to behave, and also and leaving blank what you don't know about how to behave. And then reinforcement learning can fill in the gaps. And it provides a nice way of structuring the value functions in order to get rapid learning. So let me just talk about meta-reasoning for a few minutes, about 5. So the other big problem, well, there are many big problems in AI, but clearly being able to do look ahead is nice, right? But you can't do too much of it because you just sit there, do nothing until you die of starvation. So there has to be some trade-off between the amount of deliberation you do to improve your decision quality and the amount of time it takes. And so the idea of rational meta-reasoning was to choose computations approximately rationally. You can't do it perfectly rationally, but at least apply some common sense to the task of choosing which deliberations to do, if any, and then acting. So roughly speaking, this is the algorithm, right? You want to do the right thinking. We treat computations as actions. So again, this notion of a joint state space between the physical and programmed state of the machine. And computations are actions that change the programmed state of the machine, but they also cause time to go by. So the reason you do them is because you want to get a better decision. So we can think of that as a benefit of, and then the cost is the time it takes. And crudely speaking, you subtract the benefit from the cost, and you keep doing the best computation, the one that has the most positive value, until there are no positive value computations left. And that's a good sign that you should stop thinking and do something. Okay? So this is a pretty general. In fact, this is the agent program. Right? If you can just figure out how to make each of these pieces operational, you no longer need to have any algorithms in AI whatsoever. Okay? That seems radical, but in fact it has to be the case. Right? It has to be the case. We don't have graduate students to invent algorithms and insert them in our brains whenever a new problem comes along. Right? When your mother or your father taught you to play chess or Go or Assassin's Creed 17 or whatever it is, right? They didn't say, well, I'm going to teach you this game, but first I have to teach you the alpha-beta algorithm, because otherwise you're not going to be able to make any decisions, right? That's just not how it works. The brain just naturally figures out, it may take some practice, but the brain naturally figures out how to allocate its computational resources to give you good decisions pretty quickly, okay, in all kinds of settings. So this was the subject of some work. This would have been Eric Wiefeld's thesis had he not passed away. And so this is mostly written up in the book Do the Right Thing. And as I mentioned, it rests on this idea of the joint state MDP, that you have the physical state and the environment state modeled in this joint MDP. Your physical actions change the physical state, your computations change the computational state, but they also move time forward in the physical world. So most of the work, and the work we did, and in fact, in general, the analogous topic of value of information has primarily looked at myopic policies, and it's been quite difficult to get past that. So a myopic policy just says, essentially, if I had to do one more computation, which would it be, right? The reason it's not obvious how to do more than that, right, is that you're trying to choose a computation. If you wanted to choose a sequence of computations where the second computation depends on the outcome of the first, you couldn't really figure out what the second one was going to do without doing the first one. But that's the whole point. You don't necessarily want to do the first one. You're trying to decide if you should do the first one. So it seems daft to do the first one in order to decide if you want to do the first one. All right? So there's this sort of problem, and perhaps you could come up with abstract descriptions or perhaps high-level computations as opposed to primitive ones. There are ways you could get around this, but this is the fundamental quandary. So let me just show you how it works for a simple game tree search. So here's a game tree you might be familiar with, straight out of AMA. Now, let's suppose I want to take that node whose value was currently 2, okay, and I'm deciding, should I expand this node? Right? Well, what's going to happen if I expand this node? Well, the value is going to go away, and it's going to be replaced by a new value, which is the maximum of its children. But I don't know what that is because I haven't done the computation yet. Right? So it's an expensive computation. I can guess what the outcome is going to be. It's going to be centered around 2, probably. Otherwise, my evaluation function is somewhat self-inconsistent. And it's going to have some variance, and that variance may depend on the nature of the state. If it's a very settled state, it'll be a very narrow variance. If it's a very wild and crazy state, it could be quite varied. Okay, have a large variance. But this describes what we might call a self-model. So meta-reasoning requires these self-models, a description of what we believe about what our own computations do. This is a very simple case because it's a depth 1 expansion, and so it's sort of a fixed computation. It doesn't, if I was going to allocate 100 nodes, then the algorithm itself would be choosing those 100 nodes, and so my self-model would be self-referential, and you'd have much more complicated kinds of convergence issues. Okay, Shlomo's telling me it's time, but I do want to get through this, so I apologize for running over a bit. Okay, so and it's relatively easy to learn this distribution, because you can do these by the billion, right? It's easy to do depth 1 node expansions and see what happens to the value of the node, right? You just do that for billions of nodes, you put them in buckets, you learn how the variance depends on features of the state. That part's easy, okay? So this is what's going to happen, right? We're going to get a new value drawn from this distribution. Now, what effect that value has, the new value, has on the decision is what matters, right? If I could show you that it could have no effect on the decision, then there would be no point in doing the computation, all right? So in this case, it can, because the current best move has value 3, right? So if this move actually turns out to have value more than 3, then we'll get some benefit, because it will become the new best move and we'll have learned something. So we'll call that the benefit of the calculation. But there's a fly in the ointment, which is the other sibling of the 2, which is the 4, and the min node will choose the 4. So if the 2 becomes a 6 or a 10, that's not going to help, because the min parent will choose the 4 instead. So the 4 is kind of an upper bound on how much benefit you can get. So we're going to have an integral over this region where the amount of improvement is the benefit, and then in this region the amount of improvement is fixed. We'll get an improvement of 1 by going from 3 to 4. Okay, so we just have a simple pair of integrals that give you a greedy myopic estimate of the value of this computation. And so we implemented this. We had some tricks to make sure this can be calculated efficiently and incrementally, and we applied it to Othello, and we got some quite encouraging results. So we weren't actually expecting to do necessarily as well as alpha beta. We were hoping to do a lot better than random. It turns out that when you're up at alpha beta depth 6, alpha beta is about 1,000 times more efficient than random growth of a tree. Okay. So what we tried to do, we adjusted the amount of the cost of time that we told the system to trade off against the benefit of computation. We tried to adjust it so that they would play roughly equally. We didn't always succeed. But you can see that here our algorithm, MGSS star, is doing better than alpha beta all the way down. And by the time we get to depth 6 alpha beta, we're using about 12 or 13 times less computation in terms of the number of nodes expanded. And interestingly, it often expanded some paths way past. So we would find paths expanded 17 or 18 or 20 nodes into the future, whereas alpha beta was bounded to 6, even though it's using a lot more nodes. So it's much more selective search. There is some overhead, so we're only getting a factor of 4 in terms of the CPU time and savings over alpha beta. Beyond this, the myopic problem kicks in. So once we were trying to play against alpha beta depth 7, then MGSS would sort of just refuse to do any more computation. It would say there's no leaf nodes I can expand that have any chance of changing my mind, so I'm stopping with this tree, right? And that tree wasn't big enough to beat alpha beta at depth 7. So this is the meta-greedy barrier, as we called it. Briefly, what happened later on, and I think almost pretty much independently, was Monte Carlo Tree Search got going. And I'm not, probably almost all of you know how Monte Carlo Tree Search works. It does random rollouts to the end of the game and measures the value of a position by how many of those rollouts lead to a win or a loss. And the key thing is that they applied meta-reasoning to choose which rollouts to do. And they said, look, we've got a bunch of choices. We could do a rollout on any one of these. Right, this is just like a random trial in a bandit problem. So let's apply bandit theory. And indeed, there are very efficient, provably asymptotically optimal heuristics, the upper confidence bound heuristics, that have really wonderful analysis, fabulous papers if you haven't read them, showing that with very simple rules, you can get close to optimal regret compared to really solving the bandit problem, which is intractable. So that was great, and it made a big difference. It wasn't the only contribution, but it was one of the big contributions that made Go work at nearly professional standard compared to very, very bad programs that used to exist a decade ago. Unfortunately, the theory, even though it's very elegant and beautiful, is completely wrong. So Solomon, I think, is here, and his student David Tolpin also noticed there at the same time. I think we were at ICAPS 11, maybe? I'm sorry? In Barcelona, yeah, right. And we just started chatting, and we sort of said the same thing at the same time to each other, and then, oh, I guess we should write a paper together. It's not a bandit problem because bandit problems charge you more if you pull the bad arm, right? So bandit problems are like medical trials. If you kill the patient, that's not as good as saving the patient's life, even though it's just a trial, still dead, okay? Whereas when you're just simulating a computation, it doesn't matter if you simulate a bad thing or a good thing. It costs you the same. It's just the time that went into it, okay? So it's mathematically a different problem, and actually that completely changes the structure of the problem. The other thing is that bandit problems play forever, right? So the whole idea that eventually you should stop and do something was missing from bandit theory, and that should have been a clue that something was wrong. So instead, there's another theory called selection theory, which goes back to about the same time, but is a quite different theory. And in our paper, we proved several things. Number one, there is no Gittins index for selection problems, so they're just different. We also showed a nice theorem, one that you would hope was true, right? That the expected amount of computation you will do is never more than the value you can get from solving the problem. Okay? So that's reassuring. Right? Later on, we'll see that it isn't always true it's not true in every case. I'm going to skip over those two theorems and show that, so when you're doing selection problems with Bernoulli arms, this was, as far as I know, the first bound on the number of samples the optimal policy takes. It turns out that for Bernoulli arms, if C is the cost of a sample, you will never do more than about 1/4C samples in the optimal policy. But it turns out that for some types of selection problems, with a vanishingly small probability, you can keep sampling forever. Even though the value of the problem itself is finite, right? It's only worth $1 to solve this problem, you'll spend $1 billion trying to solve it, right? And still be optimal, okay? Which is a peculiar thing, but it just happens. Okay, so now I'm just going to go very quickly over some mysteries that have been puzzling me, and hopefully they will stimulate some ideas in the audience. So one mystery is this, right? So I told you all about these angelic actions, and the angelic postconditions follow from the fact that the high-level actions have multiple ways of being implemented. Okay? And they correspond to multiple primitive action sequences. If you look at every IPC domain, every planning problem ever described in this conference, those actions are not physically primitive actions. Right? They are high-level actions. So, the blocks world, pick up a block and put it on another one. That is a high-level action, because there's, with a real robot, there are many, many, many ways, as you know, if you work with real robots, to actually do that. Okay? And those actions can have different effects. PDDL doesn't have angelic postconditions. So something is wrong here. Right? You're all describing high-level actions. All your high-level actions have many, many possible implementations, but somehow they're not represented. The multiplicity is not represented in the language. It can't be represented in the language. So maybe it's just magic, right? Maybe that in the real world, for every action in every planning domain, no matter how you implement it, it has the exact same effects. If that was true, then you wouldn't need angelic postconditions. Okay? Could also be the case that because of the inability to represent angelic postconditions, the planning community has actually focused on a tiny subset of real-world problems that happen to have this magical property. The third possibility is that you're all lying, right? That the PDDL representations you're writing down are just false, okay? And that's a problem. So some combination of these last two things, I think, is what's going on, right? I don't think the first one is right. Okay. So put another way, right, if you start from the bottom and work up, you start from really primitive actions, however far down you want to go, and then work up to build actions that achieve complex goals, what happens to the angelic postconditions? Where do they go? Right? If you allow them, then presumably you can be truthful about more domains. You're not forced into falsehood quite so early as you would be if you were just using PDDL. Okay, I think that's my last puzzle. I'm going to stop there and apologize for running over. Thank you.